Today's video is on the Vesper theory, and Vesper stands for valence shell electron pair repulsion. So all of these covalent compounds that we see in the world take on these different geometric shapes like linear, AB2, trigonal planar, AB3, tetrahedral, AB4, trigonal bipyramidal, AB5, and then octahedral, AB6. Now each of these geometric root shapes have derivatives. So these are all the derivatives, and derivatives come about because of the lone pairs. The lone pairs will squeeze the bonded angles, causing different geometric shapes and angles along with them. So we'll go through each one at a time. Starting off, a lone pair also noted will cause a 2.5 degree squeeze on the bond angles. Once again, we're going to go over the root shapes and each of their derivatives as we move through each candy modeling. So here's my modeling kit, and you can all certainly do this as you go through your building your structures. We're going to start off with AB2. In AB2, we're looking at two bonds around the central atom. And in making those two bonds around the central atom, you have here a linear shape, and that linear shape is 180 degrees. The bond angle is 180 degrees, okay? So now we move into AB3. In AB3, we're looking at three bonds around the central atom. In doing so, we make a geometric shape that's called trigonal planar. Notice it makes a triangle. You connect all those ends, it's a triangle. And if I move it over here, you'll notice that all the bonds are on a flat single plane. Okay, so this is why it's called trigonal planar. And the bond angles are all 120 degrees far apart from each other. So the next one we're going to do is the derivative, and derivatives are going to be represented with lone pairs, and lone pairs are your marshmallows. So now in this derivative shape, this lone pair is going to cause the 120 degree angle that was originally there, a squeeze of 2.5, which now means that this new shape called bent is 117.5 degrees. So this bond angle is 117.5 degrees. Moving to the next geometric shape. The next root shape is AB4. This is a very popular root shape because you're fulfilling what is called the Octet Rule. In AB4, we have four bonds. In order for us to accommodate that fourth bond, we move the three bonds downward in the AB3 notation, and you'll see a pyramid shape, and then we'll put the last bond on the top. And a way we think of this shape is a three-legged alien or a tripod. So you can think of it in any of those two ways. Now, if you want to check your structure, to check it is to make sure you put it on a flat surface, and then you make sure that the head of the alien or the tripod is always perpendicular. So it's hard to see it from your angle, but I'm going to rotate it and always see that this head right here, the head that's sticking towards you, is perpendicular to the surface. And when you do that, you have to rebond if it's not. So push that bond in, and you'll notice that you've made a really nice tetrahedral shape. Now the bond angles are all greater than 90, obtuse, 109.5 specifically, as far apart from each other as possible. So they're all equal angular, 109.5 degrees from each other. Let's go ahead and make the derivative, AB3E. AB3E means there's a lone pair on one of the bonds. And once again, the molecular geometry is, in fact, trigonal pyramid with 107 degree bond angles right here. So it looks like a pyramid. Again, this lone pair shifts these bonds downward just ever so slightly, 2.5 degrees, causing these bond angles all around to be 107. Now, why is this called a trigonal pyramidal shape? Ignoring that lone pair, you'll notice the pyramid, the bonds going downward right here, making a pyramid shape, and here's the apex of the pyramid. So again, this is called trigonal pyramidal. Now we go to AB2E2. So now I have two bonds and two lone pairs. So looking strictly at the bonds, you'll notice the shape and geometry of this is called bent, because it doesn't look quite like a line. It's been bent down by those lone pairs. And so the angle, instead of 109.5, which is its root shape, the angle is twice the squeeze from the two lone pairs, which means it's a 5-degree squeeze on the bond angle. So what's 5 minus, or subtracted from 109.5? It is 104.5. Moving on to the next geometric shape. The next geometric shape is in fact AB5. I'm going to create this electron geometry, AB5. Now the way I do AB5 is I first start off with AB3, and then I put, once I do AB3, you'll notice a trigonal planar shape, okay, trigonal planar, and then I figure out where would I put the last two bonds, because it's AB5. So I put it on the top of the trigonal planar shape, and I also put it on the bottom, the next bond on the bottom of that trigonal planar shape. Notice that by putting the bond on the top and bottom, which is on the vertical plane, you'll notice that the bond is now perpendicular. So there's a 90-degree angle in this shape. And there's also 120 because, remember, we started off with that trigonal planar shape. So all around here is a trigonal plane, or 120 degrees. So we call this shape trigonal bipyramidal because we see a pyramid on top, and then if we flip it, we see another pyramid on the bottom, or on the bottom of that same shape. So this is called a trigonal bipyramidal shape. Now we're going to do derivatives of those shapes. So we're going to start off with AB4E, and AB4E, we put a lone pair along the 120 degrees. We don't put it on the 90 because the 120 gives us more space for repulsion, or more space to minimize the repulsion. So putting it along the 120, which is the horizontal axis, we'll notice here we made an interesting shape called a seesaw. So the seesaw is in fact there's two different bond angles. Because we have this lone pair along this trigonal planar area, the horizontal plane where the trigonal planar is, this angle right here is no longer 120, it's 117.5 degrees. This lone pair also causes the perpendicular angle, which is 90, to be 2.5 degrees less, which is 87.5 degrees. So now we go to the next derivative. The next derivative is our T-shaped, and once again, we are going to place our lone pair along where the trigonal planar, or horizontal axis, where the trigonal planar is. So I find where my trigonal planar is. Here's my trigonal planar. And I'm going to put the lone pair anywhere between the two bonds. So I'm going to choose this left bond. And now I have a shape that you can see by the letter T. So it's called a T shape. So again, T, the letter T. So the angle for this is no longer 100 or 90. It's now got two lone pairs causing repulsion on both ends, twice the repulsion. So now it's 85 degrees. Because of the two lone pairs squeezing that 90 degree by twice the 2.5 degree squeeze. Now we do our last one, which is AB2E. So in AB2E, we're looking at, again, trying to utilize where there's a lot more room. The lone pairs like to take more space. So now we have a geometric shape that is accordingly. So connect this. You'll see it's linear. It's a line. So it makes a line. And so the repulsion from all three of these bonds right here will equally repel the top as well as the bottom. And so this bond angle is 180 degrees in this linear shape. Now we're going to do all the derivatives for AB6. So AB6 is where no longer will I see a trigonal planar shape. I'm actually going to make a square planar. So in my square planar shape, all the bonds are perpendicular to one another. So here's my square planar. Notice if I connect all four ends here, it makes a square. And then again, I'm going to think about the last two bonds because there's 6 total bonds in this electron geometry, AB6. So I put it on the top and I put it on the bottom, the last 2 bonds. And notice how all the bonds are perpendicular to one another. So it's all 90-degree right angles all throughout this whole structure. We call this structure octahedral because there are 8 faces to this structure, and you can actually count the faces. Here's 1 face, 2, 3, and 4. And then if I flip this structure the other way, 5, 6, 7, and 8. There are 8 faces, and thus this is called octahedral. So now we're going to do a derivative of that octahedral shape. In the first derivative, AB5E, I'm going to put the lone pair, and we don't have to really decide where to put that lone pair because they're all 90 degrees apart from each other, so they're all equal distance. But upon doing that, you'll notice the geometric shape coming out of this, which is called square pyramid. So it's a square base. Here's your square base. And notice the last bond sticking right perpendicular to that square base. So this is called square pyramidal. And the bond angle, because of this lone pair that sits on the bottom, instead of 90, is going to squeeze these bonds upward to make it 87.5 degrees. Now we go to AB4E2. In AB4E2, we do have to specifically put that lone pair on the top because, again, you're trying to spread those lone pairs as far apart from each other as possible, and they do take up more space. It doesn't make sense to put them on these where the square planar part is. So we put it on the opposite end, and in doing so, we make a flat square plane. So we call this square planar. And all the bond angles are 90 degrees because the repulsion from the top is going to be balanced out with the repulsion from the bottom. So whatever is being repelled from this lone pair on the top, pushing these bonds downward, will then equally be repelled by the lone pair on the bottom, pushing it back towards on the plane. So this is why the bond angle is 90 degrees for a square planar shape. Now we go to AB3E3. So in AB3E3, we just add another lone pair along the square planar part of this structure. And in doing so, we have a very similar shape that we've seen before, and it's called T-shape. So here's our letter T. And T-shape here, the angle is due to this lone pair right here. And this lone pair is going to squeeze this 90-degree angle downward by 2.5 to make it an 87.5 degrees bond angle. So this bond angle is 87.5 degrees, as well as this right here. Now we go to our last derivative. Our last derivative is AB2E2. And in doing that, we put the lone pair on the opposite end where we put the lone pair prior. And now we have you can see it, a line. This is a linear shape. And in this linear shape, the bond angle is 180 degrees. I hope you practice building these structures, and they're all the electron geometries and their molecular geometries. In other words, all their root shapes and their derivatives.